Transition metal complexes. A complex consists of a central metal ion surrounded by ligands. So to put that into context, at the bottom of the page, the top two we would have said would be ligands, these two top diagrams, whereas here, where we've got the central metal, put in both of these, would be a complex. A ligand is a molecule or negative ion which bonds to the metal by the donation of one or more electron pairs into unfilled metal orbitals, i.e. they form dative bonds. The most common neutral compound to act as a ligand is water, which bonds to the central metal ion through one of the lone pairs on the oxygen atom. Ammonia, NH3, is also a neutral ligand, bonding through the lone pairs on the nitrogen atom. Common ligands that are negative ions include cyanide, halides, nitrite, and hydroxides. So if we have a look at each of these, we can see how they have the chance to datively bond. So the ligands which have been mentioned are water, ammonia, we have mentioned cyanide, halides, the nitrite ion, it's got a strange kind of 1.5 bond system going on down here, but we'll worry about that later, and the hydroxide ion. Okay, so if we have a look at the number of electrons around each of these, oxygen has got 2 lone pairs, or the oxygen and water has got 2 lone pairs of electrons. The nitrogen has a lone pair of electrons. In cyanide, this nitrogen has a lone pair of electrons. Fluorine has got 7 electrons. So that's 3 lone pairs there, but because it's F minus, it's gained this extra one. So there's actually 8, and that would be the same for all of these as they're in the same group, obviously. The nitrite, the nitrogen and the nitrite has a lone pair. And the oxygen has 6 electrons round about here. So in each of these instances, I should add that these are negative. As will these ones be in square brackets with the negative sign. Ligands such as cyanide, water, and ammonia and other molecules are negative ions donating 1 electron pair to the metal ion, so that's forming 1 dative bond with the metal ion, are said to be monodentate. Those that donate more than 1 electron pair are polydentate. The term dentate is derived from the Latin word for tooth, and so monodentate ligands can be considered as one-toothed ligands. Ligands are also said to be chelating, from the Greek word meaning claw. If the ligand has two lone pairs, it's called a bidentate chelate. Common bidentate ligands are the ethane dioate, otherwise known as oxalate ion, and 1,2-diaminoethane or ethyl-diamine, both of which are shown below as the ligand itself and then chelated with cobalt. Looking at our three monodentate ligands, which it just mentioned, this is where this lone pair of electrons is where this would bond datively onto a metal, so for example cobalt. Here, although it looks like it has two lone pairs of electrons which would attach, and then that would maybe be called bidentate, not monodentate, actually because water's so small compared to the size of a transition metal, there is actually only space. It couldn't reach from two angles to actually form two bonds, so it tends to only attach with one of its lone pairs. For consistency, we'll just say onto cobalt. The nitrogen again will datively bond using this lone pair of electrons onto your transition metal. Your oxalate ligand, which is said to be bidentate, and some of you, if you did the potassium permanganate oxalic acid experiment for your higher assignment, may well be aware of this. If it's oxalic acid, it would have the two OH groups there, so that's what's found in rhubarb. Well, the oxalate ion is this with its negative charges, and its lone pairs on the oxygen, which are here. Now, because these are a little bit further away, you would then have the opportunity for two dative bonds to be formed. So it can kind of wrap round that cobalt. The other ligand, which is the 1,2-diaminoethane, is shown like this in the notes. And you may or may not have had this explained at higher, but this is definitely part of advanced higher, is converting this into a full structure. And all we're really saying is that every time you get a little corner like this, then that's a CH2. But in this instance, you've always got, if we move that slightly how we're drawing that and put our hydrogens on, you have this lone pair of electrons here, and the same at this side. And because these angles, these bonds can just rotate, you have the chance that this 1,2-diamino ethane can then again wrap round. So one dative bond here, and then you've got that's the nitrogen, and then you've got this 2-carbon chain that can then wrap around to this next nitrogen, which can bond again datively onto your metal. A common reagent or chemical used in volumetric analysis, so that would be titration, is ethylene diamine tetraacetic acid, unsurprisingly shortened to EDTA. EDTA is hexadentate, and this hexa means it would form 6 dative bonds onto a central metal ion. And it complexes with many metals in a 1-to-1 ratio. So this is EDTA over here. It's this shortened structure where each of these little bits is a CH2. So you can see that we've got 4 acid groups round about here. And each of those acid groups, when it ionises in aqueous solution, will lose each of those hydrogens on our acid group and we'll be left with a negative charge here, which means that we end up with a lone pair of electrons hanging around here, ready to wrap round and attach on. The other place we've got the possibility for the lone pairs is here on our nitrogens. So by the time you combine our oxygen lone pairs, there's 4 of them, and the nitrogen pairs, we have 6 different places where EDTA can datively bond onto a central metal ion. And that's what we're seeing here, where this structure, the black lines, are all the black lines from this bond, and it has wrapped round this central metal. This is an octahedral complex because of that shape that we learned about in VSEPR, where we've got the square planar bit in the middle and then the bipyramidal shape either side. So we've got 2 square base pyramids with this EDTA kind of clawed round about the outside. As well as analytical uses, EDTA has a number of commercial uses. It can be found in sodium salt in many products such as soap, beer and mayonnaise. The EDTA is used to trap transition metal ions that could potentially catalyse the decomposition of the product. EDTA is the most commonly used anticoagulant in evacuated blood tubes used for submitting blood samples. So if you've ever given a blood sample and you have that little tube, a kind of test tube type thing that your blood gets put into, then you may well notice there's already a liquid in the bottom of that before your blood gets added, and then the nurse will shake like mad to ensure that that's mixed through, and that solution in here contains some EDTA. It inhibits the clotting process by removing calcium ions from the blood. The chemical has been used to prevent clotting in blood specimens since the early 1950s and has certain advantages over other anticoagulants. EDTA's most distinctive character is that it does not distort blood cells, making it ideal for haematology use. Another weird use of this is it's generally used to sprinkle over meat products. Because it stops the clotting, it keeps that bright red look to fresh meat, and it stops meat going brown. So if you ever open packs of meat and it's very red, the chances are it's just got lots and lots of EDTA on it. Moving more into biology, the heme group, or part of a hemoglobin molecule, contains an iron atom at its centre, complexed with a tetradentate ligand, or 4 lone pairs bonding. So you can see here the nitrogen's already got 3 bonds, which means that this bond here, this dative bond, is a lone pair of electrons. And that's the same here, here, and here. Below is the chlorine section of the chlorophyll molecule, or the chlorophyll A molecule. The box shows a group that varies between chlorophyll types. But having a look in the middle here, we've got the same deal where we've got elements that can free up lone pair of electrons to attach into a central metal ion. Note the marked similarity between the heme group and the chlorine section. The difference in colour of red blood cells and green chlorophyll is due to the different metals to which these groups are chelated. If you note the marked similarity between the heme group and the chlorine section, where this ring structure is remarkably similar comparing the two, and that would be a product of evolution. There are other reasons for the differences in these colours, but one of them for sure is the metal ion at the centre and the effect that has, which we will come back to later. The other difference is due to the structure of this heme group and how far that structure extends, and we'll cover that effect in the organic unit. The number of ligands in a complex ion varies depending on the particular ligand. For example, in this copper water ligand, which by the way is wrong, the formula is incorrect. That formula should be, I must have missed this one when I've updated the notes because this changed last year. That formula would be OH2, 6, 2 plus. The copper 2 ion is surrounded by 6 water molecules, and in copper chloride there are 4 chlorines acting as ligands around the copper ion. The number of bonds from the ligand to the central metal ion is known as the coordination number of the central ion, and in the two examples given above, the copper 2 ion has coordination number 6 and 4 because there are 6 water molecules attached to the copper, and here there are 4 chlorines attached onto the copper. So the magnesium in this section, in the chlorine, the magnesium has a coordination number of 4, iron's coordination number of 4 in heme groups, and in this with the EDTA metal complex, this complex would have a coordination number of 6. Naming complex ions. Complex ions are named following the IUPAC, which is the International Union of Pure and Applied Chemists, and the rules are complex, and unfortunately for us there are no videos out there apart from the ones in Hindi which follow the IUPAC rules. This has changed recently, so most past papers, in fact all past papers, will be incorrect because there is none released for last year. So hang on to your hats folks, this may be a tough ride, but I promise you this gets easier as time goes on. It's purely a case of practice. So rule number 1, if the complex is a salt, the name of the positive ion, which is a cation, precedes the name of the negative ion. So we'll come to this word first, the cation. So if we have a look at electrolysis, we've got our positive electrode and our negative electrode. The positive electrode is known as the anode. The negative electrode is known as a cathode. And you all know that negative ions would move towards the positive because opposites attract, and positive ions would move towards the cathode. So that makes negative ions anions because they're attracted to the anode, and that makes positive ions cations because they're attracted to the cathode. I do know that this looks like cation, but I promise you it's not. It's definitely a cation. So that comes back to the positive ion precedes the name of the negative ion. And remember a few videos back, I said to you that the positive coming first, or the positive ion being first in the name, was going to become important in advanced higher chemistry, and this is the point that that's the case. Rule number 2, the name of the complex part, ion or neutral, consists of 2 parts, written as one word, no spaces. The ligands are named first, and the central metal ion is named last. Rule 3, the ligand part. The ligand name is preceded by the Greek prefix, which is what you've been doing in chemistry for ages, with your mono, di, tri, tetra, penta and hexa. If more than one ligand is present, they're named in alphabetical order, ignoring Greek prefixes. So, relating that rule to organic molecules, you've already been using that rule, although you might not be aware of it, but if we could just go over that again, you'll see what I mean. So, we have here, we've definitely got an alkane. We've got 1, 2, 3, 4, 5, 6. So it's some form of hexane. We then have, we've got ethyl groups, and we've got methyl groups. So we're going to put them in alphabetical order based on the ethyls and the methyls, regardless of how many of each of them we've got. So our ethyl will go first, before our methyl. Then we need to see how many of each of them we've got. So we've got 3 ethyl groups, so that would be triethyl, and we have 2 methyl groups, which makes that dimethyl. So then you can see that we're not taking into account this for alphabetically. We're sticking with the names of the groups that we're adding on. Just for completeness, we'll pop in the numbers for that. So our dimethyl are going to be on carbon number 2. And our trimethyl or triethyl will be on carbons 3, 3 and 4. So we've got 3, 3, 4, triethyl, 2, 2, dimethyl hexane. So that's what we were saying here, that if more than one ligand is present, they're named in alphabetical order, ignoring the Greek prefixes like you have previously done for carbon compounds. Common ligand names are shown below. So here we've got the formula of the ligand, we've got the normal name of the ligand, most of whom you should know. So you should know your chloride, your oxide. Cyanide we've talked about already. This is definitely one to learn. Oxalate, again, you're going to have to learn this one. Ammonia you should know. Water you should know, although please note we're writing it the wrong way round. We're writing it a different way round, because it's always the element or the atom that's forming the dative bond that's written first. So because that's where our lone pair's coming off, that's what gets written first for our OH2. Carbon monoxide is carbonyl, or carbon monoxide, CO, and hydroxide is OH. This end sounds horrendous. So chloride becomes chlorido, and oxide becomes oxido. with cyanide becoming cyanido and oxalato and amine. Now we've put in here there's two M's. I have not misspelled that. That's not amine, it's definitely amine. Amine is NH2, amine is NH3. Aqua, we're going with the kind of Greek. For water, the carbonyl stays the same, thankfully, and hydroxide becomes hydroxido. In other words, if you have a negatively charged ligand, the E at the end just gets replaced with an O. So if you can imagine chloride with the E just becomes chlorido. And that follows true all the way down. Oxalate is just oxalato. And the rest of them don't have negatively charged. Oh, that is missing. There you go. OH negative for the hydroxido. The metal part, rule number 4. The metal name is followed by the oxidation number in brackets. The overall charge in the complex part will be equal to the sum of the oxidation number and the total charges on the ligand. This is very similar to what you've been doing for calculating the oxidation state. The only other thing I would say is that this is in Roman numerals. So if you're used to thinking about things like copper 1 oxide, then you would be used to having the copper being related to the Roman numeral charge. If the complex ion is a negative ion, the metal name is followed by the suffix -ate and then the oxidation number in brackets. Unfortunately, there are no simple rules for going from the name of the metal to the name of the anion. Sometimes Latin names are used. Check the symbol. Sometimes the name ending of the metal is dropped. Common negative ions names are shown below. So vanadium becomes vanadate, chromium becomes chromate, manganese is manganate, then we've got ferrate, cobaltate, nickelate, cuprate, stannate and plumate. So most of these agree with what their actual symbol is. So instead of iron, which we know is Fe, we're moving back to the Latin name and referring to our iron as ferrate, hence the Fe. Cobalt's fine, nickel's fine. Copper's not Co because that's cobalt. It comes from the name cuprous, so we're going to head to cuprate. Tin is Sn from the name stannum or stannate in this case. And lead's Latin name is plumbum, so we're going to call it plumate. So that sounds totally horrendous, but I promise you it will start to make sense. I'll work through a good few examples with you before I leave you to do your quick test. So this is the first complex that we're going to have a go at naming. I'm not going to talk you through the way it is in the notes. I'm going to name it as I would name it, and hopefully between what I do here and what's in the notes, this will start to make sense. So the very first thing I do is have a look purely at what's going on. So we've got potassium first, and the first part of this is just the potassium, and the second part of this is the complex. So I said previously that whatever's first is positive and whatever's second is negative. Because this complex is negative, that means it's rule 5 that we need to deal with, which means that this is going to get our funny Latin names. The first part, though, is really easy because it is literally just potassium. And it doesn't matter that the 3 is here. Then we have a look at the rest of this. So naming this complex, we're going to have a look. We've got 2 parts to the complex. If we have a look at the ligands, we have cyanide ligands, and we've got 6 cyanides ligands. The 6 will become hexa, and because cyanide is negative, then this E is going to convert into an O, so this becomes hexacyanido. According to rule 2, we need to have ligand first and then metal. So that means that we're going to have our hexacyanido followed by the name of the metal. Because it's a negative complex, we're then going to take on the Latin names according to this rule 5. So our Fe for iron is going to turn into ferrate. So we've now got potassium, hexacyanido, ferrate, and in all of that there's only one space, which is there, although I didn't make it very big. And the only thing that's missing at the end of this is the charge. So what number is going in those brackets? So to do that, we need to have a look back at the oxidation states and see what's going on. So looking at our formula, we've got K3. So we know that potassium has a +1 charge, so that K3, the whole thing, will be +3. We've got our Fe, which we don't know the charge on, and that's a lot of the problem is this. We need to find out what's the, it's not the charge overall, because up here there is no charge, so that we know that the whole thing here is 0. So coming back down to this, we've then got these cyanides, and we said earlier that they were negative, and there's 6 of them. So that's going to be 6 lots of -1, so that's -6. And the whole lot is going to equal 0. And the only way that this is possible, with our charge on the Fe thrown in, is if that Fe has a charge of +3, which then means that the number that goes in here is the Roman numeral 3. So this complex up the top was potassium hexacyanidoferrate 3. The next example I'm going to show you is naming this complex here. So as before, we've got the complex here. And because that's first, that must be the positive part. And this second part is the negative part. So we've got this salt. Because this is first, we're not going to be entertaining any of those weird 5 rules. So this isn't going to be a cuprous something or a cuprate. This will just be copper in the name. So we know we're going to have something or other copper. And these ligands will be named before the copper. And at the end, all we're going to have is chloride. So that bit's nice and easy. But what we're missing is the name of all the ligands to go in here and the charge. Okay? So, from these ligands, we have 4 ammonia ligands. So that becomes tetra, and the ammonia ligand is amine. Please be aware that we do have that double A, double M, and it's marked incorrect if you don't have that. So we now have tetra, amine, copper, something, chloride, but what's the charge? So, looking at this formula again, we need to find the charge on the copper. So that's back to working out the oxidation state that we were doing in a previous exercise. We've got 2 chlorines, so that's 2 lots of -1 because the charge on the chlorine is -1. We've got the charge of the copper, and ammonia has no charge, so that's 4 lots of nothing. And all of these charges together over the whole compound will be 0. So solving that, we've got our copper plus nothing, -2 equals 0. So copper must equal +2. So now the full name of our complex is tetra amine copper 2 with no spaces chloride. This complex here is known as cisplatin, and it's a cancer drug. In the notes it talks about the cis part of this name, just a little bit, touches on it, but I'm not interested in that just now. What I'm interested in is the naming of this actual complex. There's no positive sodium atoms or ions in front of here, so we can't say for sure that we've got a positive and then this would be negative. Nor is there any chlorides or bromides or any negative ions afterwards to force this into being positive. So the only thing we've got for this charge is to have a look up here, and there is no charge, which means overall this whole thing has a charge of 0, which means it's not negative. Therefore we're not interested in the weird naming of the metals. So this metal name here, that PT, is simply going to be called platinum. Having a look at the ligands, we've got 2 chloride ligands and we've got 2 ammonia ligands. So the names for those parts will be chloride is negative, so we're going to lose the E and turn that into an O. So we'll have dichlorido. And over here, ammonia will be called the amine ligand. So we'll have diamine, remembering the two M's. They're going to go in alphabetical order by the name of the ligand, not the bit in front. So that will be diamine, dichlorido. The ligands are named prior to the metal. So we'll have diamine, dichlorido, platinum. And now the only thing that's missing is the charge. So having a look at this and going back up to that original formula, we've got our platinum. Don't know the charge on the platinum, but what we do know is that we've got two negative chloride or negative chloride ligands. Ammonia has no charge, and the whole thing equals 0. So solving that, our platinum minus 2 is going to equal 0. So our platinum must equal plus 2, which means that charge in there is a 2. So we have diamine, dichlorido, platinum 2. This complex here, it's not in the notes. I thought I'd just give you a few examples that weren't. So we don't have a salt because although we've got a positive ion, we have no negative ion. So we're literally just looking for the name of this because this is positive. The metal that's at the centre of this is not going to have any strange Latin names. It's simply going to be chromium. In our name, our ligands will be named before our chromium, but to sort them out, we'll have a look at this. So in our ligands, we've got 2 chlorides, and we've got 4 water. So converting them into their names, their correct names, our 2 chlorides will be dichlorido, because chloride is Cl negative, so we lose the E and turn that into an O. Our 4 waters will be tetra aqua with the double A. So putting that all together and remembering that we name these alphabetically based on the name of the ligand when we're going into the name, we will have tetra aqua, dichlorido, chromium, no spaces, and then all that's missing, all that's missing is the charge. So having a look back at that formula again, we've got our chromium, we've got 2 chlorides, we've got 4 waters, but water has no charge, and the whole thing equals +1. So if we solve this, we've got chromium minus 2 plus nothing equals plus 1. So our chromium must be plus 3. So all that remains is to put our 3 into the name. So that complex is tetra aqua dichloridochromium 3. It's an interesting one to note because it highlights the fact that the ligands are always in alphabetical order. So they're alphabetically here, so the chlorine comes before the oxygen based on the first letters here. But they're not in the same order in the name because our aqua is coming before our chlorido. So regardless of whether you're writing the formula or you're writing a name, all you need to remember is that the ligands go in alphabetical order. But you don't need to remember, is that alphabetical order in the formula or is that alphabetical order in the name? They are both just straight in alphabetical order. Here we have another example. We don't have a salt because we only have one negative ion. There's nothing positive before it. Because it's negative, this chromium is not going to stay as chromium. We're going to have the Latin name. So that's going to become chromate. We name our ligands prior to our metal. So those names are going to head over, or the name of that bit is going to head over there when we're done. But we'll name it over here for now, just for space on the board. So I've got 4 hydroxides, and hydroxide ions OH negative, which means this E is going to be lost and that will turn into an O. 4 is tetra, so the name of that part is going to be tetra hydroxido. Now we need to find out what's the charge on the chromium. So overall, our charge, we've got our chromium, we have got 4 -1 charges, and the whole thing equals -1. So our chromium minus 4 equals -1. So our chromium must be +3. So the whole name, when we put it together, so remember, ligands are getting named first. We have tetra hydroxido chromate, and then the charge on that chromium, 3. This one looks horrific, but if we just take our time with it and follow the rules, we will be fine. So, we've got a complex, or we've got a compound made from 2 complexes. Our first one is always positive, and our second one is negative. So if I split the board just now, so we can keep track of what's going on either side. In this side, that platinum is just going to be platinum because it's positive. However, this side, that platinum, will be platinate, the Latin name. On this first side, we've got 4 ammonia ligands. So that becomes tetraamine. And over this side, we've got 4 chlorides. So that would become tetrachlorido. So now it's just a case of working out what's the charges on each of these. We know, because there's no balancing numbers either side, that these charges, although positive and negative, will be equally positive and equally negative because there's not a multiplier after each of them. So when we work out our charges, they should be the same, just opposite signs. So let's take the first one. We've got our platinum and we have 4 ammonias. And ammonia has no charge. So simplifying this side, we can get rid of this. We're not interested. We've just got the charge of the platinum. And that's going to be equal but opposite to the charge on this side. So over here, we've got our platinum and we have 4 -1 charges. Having a look at this now, we can cancel out this side or simplify this side. So we've got whatever the charge on the platinum is, -4. And remember, we have to have equal charge. So whatever the charge is over here, it's got to be equal to the total charge over here. This has got to stay negative and this has got to be positive. So this platinum cannot be, the charge on the platinum cannot be any larger than 3, or this would not stay, or this would not be negative. So if we work it out at 3 and we make that 3 plus, over here, if this is 3 plus, then that would be only -1, and they're not the same. So that doesn't work. If we drop it to 2, if we make this one 2 plus, and then this one is 2 plus, -4, then we end up with -2 overall. And that's the point that we have our charges being equal but opposite. So now our total name is tetraamine platinum 2 tetrachlorido platinate 2. Sometimes you're given the name of a complex and then asked what the formula is. In some ways this is easier. So having a look at this, we've got this first bit, we'll just start at the beginning. Pentamine. So we know that we have NH3 and there are 5 of them. We've got an aqua, so we've got a water, but remember that goes in the other way round, so that's OH2. We've got the cobalt. Because it's 3, the cobalt has a 3+ charge. The order that these would go in the formula is the cobalt goes first. So we'll keep that 3+ in for now. Next in order, alphabetically, but not alphabetically by this, but alphabetically by the first letter of the ligand in the formula. So because N is alphabetically before O, our formula is going to be NH3, 5, OH2. And now we need to work out, when we put our square brackets on, what charge is going up here. So we need to have a look at the whole charges, or all of the charges, to find out whether or not the 3+ that's here is affected by any of the ligands. So we've got our 3+. From the cobalt, ammonia has no charge, so 5 lots of no charge makes no difference. Water has no charge. So in total, the whole thing adds up to +3. So now our final answer is, we've got cobalt, we've got our tetraamine, there's our aqua, and we've got our charge on. Here we've got another example of writing a formula based on a name. So we've got a salt here, so our complex, which is the bit at the front, is going to be positive, and sulfate, as we know, is negative. The sulfate bit's pretty easy. We know that that's SO4, and the charge of 2 negative is going to be important. Having a look at the rest of this name here, we've got amine, so we know we've got an NH3, there's just one of them. We've got tetra aqua, so we're going to have OH2 4 times, and we've got a chromium which has got a 2+ charge on it. So now what we need to do is get these all in the correct order. So the first thing that goes in the formula, or the first thing that goes in the square brackets for the ligand, would be the chromium. And then our ligands are going to go in, but they need to go into the formula alphabetically based on the nitrogen and the oxygen. So they're going to be going in as NH3 and then OH2 4 times. So they're actually staying in the same order as the name was given. Then what we need to have a look at is what charge is all of this together. So we know we've got a +2 from our chromium. Ammonia has no charge, and water, even though there's 4 of them, has no charge. So this whole thing is 2+. Looking at a charge on the sulfate, that is 2-. If we think about these as a valency, you don't need to multiply any because they will cancel out. So remember, if you had element X and element Y and they both had a valency of 2, that when you cross them over and vanish, they would go. If, for example, this had worked out with a valency of 4+, then what we would have had to do is exactly the same way as if you were dealing with a valency in an ionic compound. If that was 4 and that was 2, when you cross them over and got X2, Y4, and then cancelled these out, then you would find that you would need 2 of that second ion. So if that had been the case for this, then we would have had 1 lot of complex, and then our sulfate would have needed to have been twice. But that's not the case for this, because this has worked out at 2+. So now our formula is literally just square brackets, chromium, NH3, OH2, 4 times sulfate.